Welcome. In this video we look at 2.6 continuity, and this is the last section that we will cover in chapter 2. Basically, you probably already have an idea of what a non-continuous function looks like. It has breaks in it, versus a continuous function. In this video we will look at that distinction very carefully. So to begin, let's talk about continuity at a point. So in this case, when I talk about a point, I really mean an x value. This function is not continuous at the point x equals 1, because when I look at 1 and I look up, that's where the break is occurring. It is continuous, however, at, say, x equals 2. If I start at the 2 and I go up, it looks like there's a nice, solid, smooth curve that passes right above the point where x equals 2. Let's make this distinction a little bit more clear. Okay, look at this graph. It's a graph that has a hole in it. It has a hole right where x equals 3. So f of 3 is undefined, does not exist. However, the limit does exist. As x approaches 3, it looks like the y values are approaching 2. Compare that with this graph. Now, in this situation, the value of the function does exist at 3. F of 3 really is 2. However, what about the limit? As x approaches 3, well, from the left the y values go to 2, and from the right the y values go to 1, so the limit does not exist. Well, they can both exist. Here's another example where the graph has a little hole, but then the function value is up above, so f of 3 actually equals 3, and as x approaches 3, those values look like they are approaching 2. But for all of these examples so far, these examples are not continuous at x equals 3. Something weird is going on. So what is the nice situation? When the graph is nice and smooth and the hole seems to be filled right where you want it. F of 3 equals 2. And the limit as x approaches 3 of f of x also approaches 2. When there's the match, all is right with the world. We have the plug-in value the same as the limiting value, and that's really what makes the function continuous at the x value 3. So here it is in general. Definition. A function f is continuous at c, and c is representing my x value, if f of c is defined and the limit as x approaches c of f of x equals f of c. So the plug-in value actually equals the limiting value. In this picture on the right, f of 3 equals 2, and the limit as x approaches 3 of f of x equals 2. That's how we know it's continuous at 3. Now we can modify this idea a little bit and talk about a function being left continuous or right continuous. This function is kind of funny, right? If it is defined at 1, and if I approach that x value approaches 1 from the left, it sort of is continuous there. So I can use a one-sided limit to talk about a function being left continuous. So f of c is defined, in this case f of 1 equals 2. And as x approaches c from the left, then I get the value of f of c. So as I approach 1 from the left, those y values are approaching 2. All right, let's talk about continuity on an interval. So far I've been talking about continuity at a point, but what if I have a whole interval of x values? So in this picture on the right, it turns out this function is continuous from negative infinity up to and including 1. So all the way up to and including 1. It is continuous on that interval. Also, I could take the interval not including 1 and going up to infinity. Everything strictly greater than 1. And on that interval also, the function is continuous. Or I could take any subinterval of that one on the right, for example, from 2 to 3. If I look at this interval, well, and I look at the function above it, sure, the function is nice and continuous over that subinterval. However, f is not continuous at this one point 1. So if I have an interval that contains the 1, say the interval from 0 to 2, no, the function is not continuous on the interval. So what is the upshot of all this? How do I know if a function is continuous on an interval? F is continuous on the open interval from a to b if f is continuous at every x value in the interval from a to b. So being continuous on an interval just means it's continuous at every point in that interval. And the same thing works if I use a half open or half closed or closed interval where I contain one or both of the endpoints. F is continuous on the interval not including a but up to and including b if f is continuous at every x value in the open interval and f is left continuous at x equals b. Okay, how about this example? Take a look at the graph to the right, and there are 8 questions that are true or false. Pause the video right now and see if you can answer true or false for all of these questions. And then when you're ready to check your work, unpause it and we'll take a look. All right, give it a try. Okay, we are back. Let's take a look at the answers. F is continuous at x equals 1. No, that is false. 2. F is right continuous at x equals 1. If I come in from the right, no, because I come in from the right, the y values drop, and then they jump up real quick. So it is not right continuous. Is it right continuous at x equals 2? Yes, it's continuous at x equals 2, so certainly it is right continuous at x equals 2. Number 4, f is continuous on the interval from 1 to 3. 1 to 3, yeah, because in that open interval, the function is defined at any point there, at any x value in there, and the function is nice and smooth, so yes, true. Number 5, f is continuous on the open interval from 2 to 4. No, because that interval contains 3, and the function's not continuous at 3. False. Number 6, f is continuous on this half closed, half open thing from 0 to 1. No, it isn't, because if I include the 0, then I'm including this one point right at 1, but then I'm also including the rest of the interval up there, so not continuous. But what if I switch the included endpoint? Number 7, f is continuous on the open on the interval that has open at 0 and closed at 1. Yeah, because now that's exactly that little segment that exists all at 2. So that is continuous there. Number 8, f is continuous on the open interval from -2 to -1. Yes, looks good. So I'm not including the right endpoint, but that's okay. True. There you go. Here's a function that is not continuous at 3, but 3 isn't in the domain. So in fact, the domain of this function pictured is everything strictly to the left of 3 together with everything strictly to the right of 3. It's the union of those two open intervals. All right, so true or false? If A is in the domain of F, then F is continuous at x equals A. Yeah, I think that's true. If you pick any value of A, as long as that A isn't 3, you can go up to the graph, and the graph will be nice and smooth and continuous above that point. So that's true. Is F continuous at x equals 3? No. But 3 isn't really even in the domain of F anyway. So if I'm really concerned about how this function F behaves, I'm not really going to care about the number 3. So we say, and we've seen this before, F is continuous on its domain. So for every point that is in the domain of F, the function is continuous at that point. And it turns out that every sort of calculus-like function is actually continuous on its domain. Now, these functions might not be continuous, but at least for wherever they are defined, they are continuous. So things like polynomial functions, rational functions, the square root of x, trig functions, inverse trig functions, exponential functions, log functions, all of these things are continuous on their domains. And in fact, that's kind of cool. That gives us a start for functions. But in fact, we can now combine functions together and still get continuous functions, or at least functions that are continuous on their domains. Here's the fact. If f and g are both continuous on their domains, then the following are continuous on their domains as well. I can add or subtract functions, multiply a function by a constant, multiply functions, divide functions, take the composition of functions, take functions and raise them to fractional exponents. So for example, in this function h of x, I have an exponential and a log, and I add them together. I can take the square root of that. I have a polynomial I can divide. And yes, despite all of these crazy ways of combining functions, I know that h of x is continuous on its domain. So what about at exactly the point x equals 2? Well, all I have to do is determine, is 2 actually in the domain of h? Does h of 2 exist? And with a little bit of work, you can tell, yes, it does. If I can plug 2 in for x down in the denominator and I don't get 0. 2 is in the domain of natural log, 2 is in the domain of e to the x, so it's in the domain of both of those. And when I add them together, I'll get a positive number, so the square root of that thing is defined. So yes, 2 actually is in the domain of h. And since 2 is in the domain of h, we know that this function actually is continuous at x equals 2. Alright, at the end of this section, we turn our attention to a well-known theorem called the intermediate value theorem. And it's an interesting characteristic that applies to continuous functions. Let's suppose that I have a function that's continuous on a closed interval. So this function is continuous at both of the endpoints and everywhere in between. In this particular example, we're saying it's continuous on the interval from 1 to 3, and f of 1 exists and f of 3 exists. As x changes from 1 to 3, the function values will take on every intermediate value from 2 to 6. Looking at the x-axis, I imagine all these x values from 1 to 3, and what are the corresponding function values for all of those things? They are all the function values from 2 to 6. And so the theorem says that if this is a continuous function, then this set of y values has no holes in it. Every possible y value will be attained at some point. Now, how we say that a little more theoretically is, given any capital L between 2 and 6, how do I know there's not a hole at L? Because I can sort of trace the function backwards, and I can find some x value, c, so that f of c is L. That's just the fancy mathematical way of saying that there are no holes in this set from 2 to 6. A lot of times the intermediate value theorem is used to show the existence of a zero of a function or a root of a function. For example, if you know that the function is a continuous function, say it's a polynomial, and it goes through the point, I don't know, maybe 1, negative 1, and then you know it goes through the point 2 to 1, then since the function is continuous, and since it has a negative value at one point and a positive value at another point, there must be some place in between where it crosses 0. Alright, so that is the intermediate value theorem, and that in fact ends our discussion on 2.6, continuity, and ends our treatment of Chapter 2 on limits.